So today we're going to be solving the May-June 2018 question paper 1-1 for physics. So let's get started with the first question. The first question asks us, what is a unit for stress? Now, this is not the normal stress that you're used to. You're stressed about exams or stuff like that. This is a different kind of stress which is defined differently. And I'm going to write the definition here. So stress is effectively the force divided by the unit area. So if I were to give you a certain area and apply a certain force on that area, we can say you're stressing that particular area. So if you want to find the units for stress, you're going to look at the units for a force, right? You're going to be like, what are the units for a force? Fundamentally, a force is defined by Newton's second law, which is the product of mass and acceleration. So you know that the units for mass are actually kgs, and the units for acceleration are ms to the power of -2. And if you divide by area, which is m squared, you're going to get kg m to the power of -1, s to the power of -2. I've just applied laws of indices here. So my correct answer is going to be A. Moving to the second question. Physical quantities can be classified as vectors or as scalars. Which pair of quantities consists of two vectors? So you need to understand what is a vector, what is a scalar, what's the difference. So a vector is basically a quantity that mainly is concerned with magnitude and direction, whereas a scalar, you're only concerned with magnitude. You don't care in which direction is going to be acting. If you look at the first one, kinetic energy and force, kinetic energy is a scalar, right? You don't care about the direction in which this energy is going to be acting in. It's 10 joules. If you're riding a bike, it's going to be 10 joules. Momentum and time is a scalar. You don't care about the direction. It's 20 seconds, that's 20 seconds. But velocity and electric field strength are actually two vector quantities that you should know. You don't exactly do electric field strength, but just important for you to know that it is a vector quantity. And weight and temperature, both of which weight is a vector, but temperature is not a vector. Moving on to the next question, we're given two dogs. So we have two big dogs that are pulling on a sledge. So Christmas, and we're at the North Pole or something like that. So we have an icy track, and with those two dogs, with dog X pulling with a certain force, that's 200 newtons. With dog Y pulling with another force, that's 120 newtons. And we've been asked, well, dog X is pulling at an angle of 25 degrees, or 65 degrees rather. And dog Y pulls with a force of 120 newtons at an angle of 45 degrees. What is the resultant forward force on the ledge exerted by the two dogs? So we want to find out what is the resultant forward force, the force that is acting forward that these two dogs independently exert. So if you're going to study this, the forward force is basically a force like this, like they've shown us here. Is a force like this that we're trying to sort of explain. Okay, so if you look at this, you have 200 newtons. You can try to resolve this 200 newtons, right? So you can see that if I have 65 degrees over here, the opposite of that, so if you were to create a little triangle like this, let me just show you a little illustration over here. If you were to create a little triangle like this and put 65 degrees here, the opposite of that, which is this thing over here, right, over the hypotenuse, so the hypotenuse is going to be, let's say here, sine 65 will actually be equal to your opposite divided by your hypotenuse, and your opposite will actually be equal to your hypotenuse times sine 65. Okay, if you look at this, we have 200 newtons acting in this direction. So that 200 is going to act as your hypotenuse. In this case, you have 120 acting in this direction, and that 120 is also going to act as your hypotenuse, which is both very important for you to keep in mind. Now, you're going to resolve these two forces, and you can see that the opposite, in this case, it's going to be this side, but you can see that this side and this side are effectively parallel, so they're basically the same thing. They're going to amount to the same thing. So what this tells you is that, hey, effectively, let's just find this component, 200 sine 65, and it's going to be the component that is going to be in this specific direction. And if we were to find 120 sine 60, sine 45, it's also going to be the same component in that same direction. 267.47 newtons. So that's the answer that you're going to end up with. And if you look at your answer, that's roughly 270 newtons. So you need to know what it is, or how do you resolve effectively. Look at the opposite. Is it the adjacent? Is it the opposite? And how do you handle such a scenario? Move on to question number 4. In this circuit, we're given an analog ammeter. If you don't know what an ammeter is, it's basically a device that measures current. And you can see on the diagram on the screen, I've showed you what an ammeter is. And it's going to be recalibrated as a thermometer. So we're going to use an ammeter for us to understand how temperature changes. So the ammeter is connected in series to a thermistor. A thermistor is basically a device whose resistance varies with temperature. So the graph shows how the resistance of the thermistor varies, and we've been asked which diagram could represent the temperature scale on the ammeter. So you're looking at this question, you're like, where do I even start? Relax and look at the resistance against temperature graph. So it shows us how the resistance R of the thermistor changes with temperature T. So as we alter the temperature of our thermistor, the resistance of the environment, rather, the resistance of the thermistor is going to change. So there's a device that basically measures current. Okay, so if you were to look at an ammeter, effectively an ammeter is going to look like that on the screen, where every deflection tells you how the current is changing, right? If you have 20 volts, 20 amps, 30 amps, 40 amps. So it's possible for you to remove that ammeter reading and put a degree Celsius there. So that implies it's still going to deflect because you've just changed the plastic label. Right, the ammeter deflects because current is moving through it. Certain mechanisms occur. So you can remove that amps tag and put a degree Celsius. So it's going to deflect because current is changing. If it deflects a lot, the current has changed a lot. Right? If it deflects very little, current has changed a little. So changing the tag from amps to degree Celsius doesn't really change a lot. So that's what we did in this experiment. So what you're seeing here are effectively from A to D are effectively ammeters, which should behave ideally, should deflect normally, but then instead of measuring amps, they just tell you the degree Celsius, the deflection at a particular change in temperature. So, but the principle is supposed to be the same. We know that V is equals to IR. So we know that resistance is inversely proportional to current. So if resistance doubles, current should halve. If resistance halves, current should double. So let's look at this. If we're at 0 degrees, we are here, we have a resistance value of R1. If we're to go to 10 degrees, which is over here. So if we're to halve our resistance value, let's go to R2. You're going to see that 10 degrees and R2 are effectively the same. So at 10 degrees, you're going to have an R2 that is of that nature. At like 40 degrees, somewhere over here, you're going to have an R3 of this nature. But the moment you get to like 80 degrees, you're not going to have a very big change. Like in your value of R. They're going to change slightly. For a change in R, because the gradient here is very shallow, here is very steep. So from like 0 to 40, you're going to have a very big change in resistance. But as you go away from that, you're going to have a very small change in resistance. So if you look at your graphs, or this relationship rather, you're supposed to have a very big change, a big drop in resistance. So you're going to have a big deflection, a big change in current, because the resistance is going to change so much. You're going to have the current changing so much for the first time period. So if you look at this, from like 0 to 20 degrees, you're going to have a very big change in current, which is very true. So if you look at A, from 0 to 20, the ammeter is going to be like true and move so much. Why? Because there's a big drop in resistance. So you're going to have a big ammeter deflection. So that's effectively what we're reading here. But as we get to bigger and bigger temperatures, we're going to have smaller and smaller deflection, smaller and smaller changes of resistance, so smaller and smaller changes of current. Does that make sense? So the correct answer is going to be A. If you look at B, B is effectively saying you're going to have smaller and smaller changes, smaller and smaller deflections at lower temperatures, which is not true, right? The current is not changing very little. It's changing a lot at very small temperatures, so B would not work. Then at C, it doesn't make sense. You can't start at fully deflected. Like, what are we doing here? The same at D, we're starting fully deflected. So your correct answer is going to be A. So keep this in mind. The resistance is going to change, so the current is going to change. The ammeter is going to deflect normally as it would, because the resistance is changing, so the current is changing. The only difference is that instead of us measuring the current, we're measuring the temperature at which that deflection occurs. So at 20 degrees, we're going to have a very big deflection because we've had a very big drop in resistance. But over time, that gap is going to get smaller and smaller and smaller and smaller and smaller. So the deflection current is going to get smaller and smaller and smaller and smaller. So the correct answer is going to be A. Move on to question 5. We're given the sides of a cube. That's a little cube, and that's a caliper. So we're going to measure the sides of a cube with a caliper. So Effectively, I like drawing little shapes here so that we can be able to understand. So we have something like this. And then we're going to measure one of the sides over here, and we're going to measure it as 30.0 centimeters. Okay. So we're effectively going to measure it, and then we're going to measure this side also as 30.0 centimeters. We're going to measure this side as 30.0 centimeters. And we've been asked, what is the percentage uncertainty in the calculated value of the volume? So you're going to ask yourself, what is the formula for volume? Volume for a cube is effectively length times width times height. But because all of these three are identical, it's just going to be L cubed. The length, side of the length cubed. And the formula that we know for finding fractional uncertainty, percentage uncertainty, is basically fractional uncertainty in V over V times 100%, sorry, should be equal to, and if we have L to the power of 3, that's a law that we use. Those are the laws, as you can see on the screen. We have 3 laws for uncertainties. So we're going to use the third one, where we have 3 times delta L over L times 100 degrees. 100%. Why do I keep on saying degrees? Okay. So we're going to have 3 times 0.1 over 30.0 times 100. And if you do the math, that's going to give you 1%. So the correct answer is going to be C. Okay. Move on to question number 6. We're given tennis ball. I love tennis. I've never played tennis before though, which is quite weird. But tennis is a very lovely sport. Effectively, you play it, against 2 people. And in this case, we're not playing tennis. We have a tennis ball, which is effectively falling in free fall from the top of a tall building. So we have a very tall building, and we're throwing a tennis ball. But there are 2 things that you must note here. The word falls freely. So let me highlight it. Falls freely, and the word in air. This seems like a contradiction, like oxymoronic to some extent, right? You're confused. You're like, falls freely, but in air. What's going on? So we're going to explain that. So falls freely means it falls without any driving force. Nothing is influencing it except the force of gravity, right? So we're not throwing it down. It's just miraculously falling freely. No external force is acting on it. Nothing at all. It just happens to start falling on its own. In air means that all of this is happening in air. It's not happening in a vacuum. So we can't neglect air resistance. The mere fact that they said it falls freely in air. Typically we say free fall means without air resistance. But in this case, we can't fall freely in air and have no air resistance. What are we doing in air if we're not going to have full air resistance? And it's a tall building. So air resistance is going to be present no matter what. And this was a tricky question, just meant to confuse you a little bit. That's why they said falls freely in air. If the question had just said falls freely, you wouldn't consider air resistance. But in this case, they said in air. So as it's falling, there's going to be air causing the tennis ball to decelerate as you fall down. So effectively, I've simplified my diagram to have that specific illustration. So my tennis ball is going to start at this specific point, and it's going to fall solely due to gravity. And it's going to start off falling. And as it falls, because there's acceleration due to gravity, its velocity is going to increase. So it's going to start off with a velocity of 0. So u is going to start off as 0. But as it falls, the velocity is going to change, maybe go to 20, maybe go to 30 or stuff like that. But then as it starts to fall, air resistance is going to increase. Air resistance is going to begin to act and oppose that specific motion. And at a certain point, these 2 forces are going to be the same. The air resistance is going to be the same as the weight. So because air resistance is going to be equal to the weight, what this means is we're going to reach what we call constant velocity. So velocity is not going to change. Okay. So this is what we just need to know on the side here. And if we go on our graphs here and we try to interpret them, effectively what we're looking for is that velocity is actually equal to the gradient of an ST graph, the gradient of this represents the velocity. So we're looking for a graph where its gradient tells us that the velocity is going to increase, then reach a constant value. And as you can see here, the gradient is the velocity. The gradient here is going to start at a 0, then it's going to increase, and then reach a straight line. Straight line means constant velocity, so the correct answer is going to be A. If you look at C, I thought at first it was C. If the question had said falls freely without air resistance, the velocity would just keep on increasing as we fall, right? The gradient keeps on getting bigger and bigger and bigger and bigger. But that's not the case because the question said falls freely in air. So we have to consider air resistance. We can't neglect it. So that was the difficulty of this question. So the correct answer is going to be A. Move on to question number 7. The graph shows the variation with mass of the weight of objects on a particular planet. So we've gone to Mars and we want to measure how the weight values vary or differs from the mass. So effectively, I know a little formula that I want to share with you guys. I think you know it too. But effectively, weight is equal to mg. Mass times the gravitational acceleration or the force of gravity. The acceleration due to free fall, or whatever you like to call it. So a graph of weight against m will have a gradient that will be equal to g. So the gradient, which is effectively the change in y divided by the change in x, will be effectively the value of g in this case, which is the acceleration due to free fall. So if you can find the gradient of this graph, we've found the acceleration due to free fall. So if we look at this, let's look at point A, which is over here, and point B, which is over there. At point B, we have 4. At point A, we have 0 for y. At point A, we have 2 point, that's 1, 2, 3, 4, 5. That's 2.5. Then there we have 0. So effectively we have 4 divided by 2.5. And if you calculate this, this effectively gives you about, divided by 2.5, this effectively gives you 1.6. Okay. So this is going to give you 1.6. So the correct answer is going to be B. Okay. Move on to the next question. The momentum of a car of mass m increases from P1 to P2. What is the increase in kinetic energy of the car? Okay. So effectively we have a big car. I'm going to choose a Bugatti, and it's moving along a straight road. So effectively it's going to start off with this particular velocity. And the velocity is going to change because the mass is not going to change, and momentum is the product of mass and velocity. So it's going to start with one velocity and end with another velocity. And you want to find out how did the kinetic energy change for that Bugatti. Okay, so let's start. So change in kinetic energy is going to be final kinetic energy, which I'm going to represent by 1/2 mv squared, minus the initial kinetic energy, which I'm going to represent by 1/2 mu squared. Okay. But there's an important catch here. The momentum starts at P1 and goes to P2. So mu will be equal to P1. Very straightforward, guys. And then mv will be equal to P2. Okay, so we can clearly see that u is equal to P1 divided by m, and v is equal to P2 divided by m. Okay, so if we go here, I can effectively say, well, 1/2 factor out m, v squared will be P2 squared divided by m squared minus, I factored out 1/2 from both of these, so I'm left with v squared minus u squared, P1 squared divided by m squared. Okay, and I can factor out m squared also in this case, so I'm gonna be left with 1/2 m over m squared P2 squared minus P1 squared, which is gonna make that cancel out. So I'm gonna have P2 squared minus P1 squared divided by 2m being my final simplified version, which is A. Two similar spheres, each of mass m, are traveling with speed v and are moving towards each other. So you have sphere A and sphere B, and they're like moving towards each other like that. Okay, so they have a head-on elastic collision. Elastic collision means they don't stick after impact. They move their own separate ways. They're elastic. It's like they go their separate ways. Okay, so which statement is correct? The spheres stick together on impact. That's inelastic. The total kinetic energy after impact is half mv squared. Okay, so we know that kinetic energy is basically 1/2 mv squared for one of those things plus 1/2 mv squared for the other thing. So the total kinetic energy is effectively going to be equal to mv squared. Okay, so the total kinetic energy after impact definitely has to be mv squared, because the total kinetic energy before impact and after impact is conserved. It's kept the same. So before and after impact, we're going to have the same value. But the total kinetic energy before impact cannot be 0. The total momentum before impact is not 2mv because they're moving in opposite direction. It's actually 0 because momentum, remember, is a vector. So it's going to have a negative for this guy. So we're going to have negative mv. And for this guy, we're going to have mv. You combine them together, you're going to have a momentum of 0. Okay. I hope I'm not moving too fast. Question number 10. We're given a horizontal metal bar, PQ, of length 50 centimeters that is hinged at this specific point. Okay. The diagram shows the metal bar viewed from above. So we're looking at it and we're like, oh, that's our metal bar. Okay. So we have two forces, one of 16 and one of 5, and they act on the end Q. What is the total momentum about P due to these two forces? Okay. Again, I'm going to resolve this 16 Newton force. I don't like how it's oriented. So I'm going to make it look like this. So if I do that, remember it's the opposite. So if I have this, it's like the opposite to that 30. So opposite over the hypotenuse, you're going to have this, all of this being 16 sine 30. Okay, so we want to find the total momentum. So we know that momentum, sorry, we want to find the total moment, not momentum. So we know that the total moment is actually equal to the force times the distance d. Okay, so the force that we have here is basically the resultant force, because we were told to find the total moment due to two forces. So we're going to have 16 sine 30 in that direction, and we're going to subtract 5, and then we're going to multiply by the distance, which is 50 centimeters, which is going to be 50 over 100, I think. 50. So 8 minus 5 times 0.5, that's going to give you 1.5 Newton meters. So the correct answer is going to be A. Okay, I hope that makes sense. Question 11. Block P and Q and S and R are made from material of the same density, but block T is made of material of twice density of the other materials for the other blocks. The cross-sectional area and the height for each of the block are shown below. Which two blocks exert the same pressure on the ground? Okay, let's have some fun here. So we know very important facts here, guys. We've learned a lot of things. So we know that pressure is actually the force per unit area. Okay, so if they're going to exert the same force, we need to have the same force per unit area. But force is actually mg. But they talked about density. Density is actually the mass per unit volume. So mass is actually density times volume. Okay, so keep that in mind. So we can substitute that and we can end up having pressure being equal to the density times volume, G divided by A. But for a particular substance, the volume is actually the area times H, like the area times H. Okay, so effectively, you're going to end up with pressure being equal to the density times the area times H times G divided by A. That cancels each other out. So you're going to have the pressure being equal to the density times H times G. Okay, so that's like the simplified version for pressure and calculating pressure. So if we start with with P, you're going to have a particular area, you're going to have a particular height. So pressure for this guy, okay, so the pressure is going to be the density times G times H. So if you look at Q, we're going to have the pressure being equal to rho GH. So P and Q have the same pressure, but we don't have the same answer, which is terrible. That's okay. If you go to A, you're going to have the pressure for this one being equal to 2 rho GH. And if you look for this, we have 2H, so the pressure is going to be equal to 2 rho GH. So R and S also exert the same pressure, but we don't have R and S in these answers, which is very sad. But if we go here, where we have twice the density, so pressure is actually 2 rho GH as well. And voila, S and T have the same pressure. Question 12. Two parallel forces, each of magnitude F, act on a rod of length 5d. Which diagram shows the position of the two forces that will produce the largest torque? So A is effectively what we call a couple. Not that kind of couple. Come on, guys. We're talking here about two pair of forces that are opposite in direction, equal in magnitude, and separated by a particular distance. We're not talking about that kind of couple. So for this kind of couple, for A, it serves as a couple. So torque for a couple is going to be one of the forces times the distance between those two forces. That's what you do for a couple. So in this case, we have F times D. If we look for B, this thing is not going to rotate. Torque is concerned with rotation. So take a pen, as you can see over there, push it from both ends, it's not going to rotate. If you do this, you're going to find out the pen is going to rotate. The same is for C, it's not going to rotate. It's like, okay, it's going to look weird. It might rotate, but it's not the same. Then if you go for D, the torque is effectively the force multiplied by 2D. So this is going to be the largest torque that we're going to have. So the correct answer is going to be D. Question 13. Liquid X and Y are stored in large open tanks. So we have very big large tanks, and we have liquid X in one and liquid Y in the other. And liquid X has a particular density and liquid Y has a particular density. At which depths are the pressures equal? Okay, so let's visualize this. So we have liquid X. So we have liquid X over here and liquid Y over here. So that's X, and density is actually 800. And then liquid Y, density is actually 1200. Okay, we have a very important fact for pressure to be equal. I've already told you and explained to you that pressure has this formula, rho GH. So for the pressure to be equal, the pressure due to X, which is the density of X, times G, times the height of X, must be equal to the density of Y, times G, times the height of Y. So effectively, the density of X, we know that is 800. So 800 G HX should be equal to 1200 GHY. And in this table, we're given H depth in X and depth in Y. So we can create some ratio and say H of X and H of Y must give us 1200 divided by 800. Okay, so 1200 divided by 800, that's effectively, if you do the math, that's 4 into 12, that's 3 divided by 2, which is 1.5. So it turns out C, that's the only one where 15 divided by 10 is going to give you 1.5. Question 14. We have a big train that's moving, and that train has a mass of 3.3 times 10 to the power of 6. It reaches a slope and it starts moving up. The slope is inclined at an angle of 0.64, and it moves up with a constant speed. The speed does not change. Now the engine is going to produce a useful power output. It's going to produce some power out, and we want to find the speed of the train. Okay, so where do we even start? Very good question. So we know this. Very important for you to keep an open mind. Power is actually equal to work done per unit time. But work done is actually force times displacement. So divided by time. And then displacement over time is velocity. So power is going to be equal to force times velocity. Okay, so if we can find the force that this little train is experiencing, and we multiply by its velocity, we can therefore find the power. And we've been given what? We've been given the power here. That we have the power, and we have mass for some reason, and we want to find, okay, we want to find the constant speed. Fine. So if you look at that diagram, if it's inclined to that angle, the mass is going to have two components. It's going to have a component moving down that is a component of mg, and you can resolve mg. So look at that illustration above. So you can have mg sine theta, mg cos theta like that, and then the force present, because it's a constant speed, must be equal to the driving force. So mg sine theta must be equal to the force going forward. So you're going to have mg sine theta being equal to F, which is the driving force here. So in this case, the power that you get out, P, is going to be equal to mg sine theta times your velocity V. So the value of V is going to be equal to, what power do I get out? 14 times 10 to the power of 6 divided by m, which is 3.3 times 10 to the power of 6, times g, which is 9.81, times sine 0.64. You punch all of this in your calculator, and you're going to get 38.756, which is effectively 39 meters per second. Okay, so just keep that in mind as you're doing these kind of questions. Look at the different values that you have and make sure that you're actually understanding what you're doing. Question 15. We're given a cannonball of mass 3.50 kilograms, which is fired at a speed of 22 meters per second from a gun on a sheep at a height of 6 meters. So we have a sheep and we're firing a cannonball of a specific mass at a speed of that from that specific height. And the total energy is the sum of gravitational potential and the kinetic energy. What is the total energy? Very easy. So that's the illustration of what's happening. The cannonball is firing a big ball at a specific speed above a certain height. So we know that the total energy is effectively the sum of the kinetic energy plus the sum of the potential energy. And the kinetic energy is 1/2 mv squared plus the potential energy, which is mgh. Okay, so we're going to have 1/2. The mass is 3.50. The speed is 22 squared plus 3.50 times 9.81 times 6. So these are the two quantities that you're adding up together to get the total energy. You're going to get an answer of 1053 joules. Roughly, you can say it's 1050 joules, which is D. Question 16. We're given an aircraft which is flying in air, but it's going to do that at a constant velocity. Okay. The diagram shows some of the forces acting on it. We have thrust, we have drag. Because they say the velocity is constant, you're going to be like, constant velocity. What do I know about constant velocity? The resultant force. So it means that the resultant force is 0. Okay. So we want to find the power produced by the thrust force. Remember, we've talked about this already. Power can be the product of the force and the velocity. So in this case, it's 2,400 times 90, which gives you approximately 2.2 times 10 to the power of 5. The correct answer is going to be B. Okay. Question 17. An electrical generator is started at time 0. The total electrical energy generated during the first 5 seconds is shown. What is the maximum electrical energy generated, electrical power rather? Okay, so what is the maximum power? That's a keyword. Generated any instant during these first 5 seconds. So what do we know about power? We know that power is actually energy per unit time. So we can say that power is the gradient. So in this case, what is the steepest gradient that we have? Is it from this point to this point, to this point, to this point, to this point? We're going to find out it's from this point B to this point C. So if we want to find the power from point B to point C, effectively we can find the gradient from those, between those 2 points. So power, change in y, change in x. And then on the change in x, which is basically from 2 to 3, that's 1. Change in y, we have about 40 joules and 10 joules. So it's going to be 40 minus 10. So I'm basically taking this point, which makes all my calculations easier. 40 minus 10, which is 30 watts. Okay. Next up, the diagram shows a wire of diameter d and length l that is firmly clamped at one of the ends A load is applied and this extends it by the length x. A second wire is made of the same material but of diameter 2d and of length 3l. What is the extension of the second wire when the same load is applied? Okay. We know that the Young modulus says the following. The Young modulus is the ratio of stress to strain. How much are you stressed? How much do you get strained? So it's going to be the force per unit area divided by x over L, which is extension per unit length. So it's the same as length over extension. Okay, so some things that you need to know with these kind of questions. If you're told that it's made up of the same material, it means that the Young modulus is the same. You know, some things you just need to know, right? Because it's the same thing. The Young modulus is unique to a particular material. So if you go here, start with wire 1. The Young modulus is going to be what force does wire 1 experience? What is its length? What is its area? And what is its extension x? But if you go for wire 2, its Young modulus is going to be the same force, but it's going to experience the same force, but the length is 3 times. So it's 3L divided by, we want to find how much it extends. So it's going to be x2. Okay. And then the area, so we have twice the diameter, and we know that area is pi r squared, which is equal to pi d squared over 4. So if you have twice the diameter, you're going to have 4 times the area, because you're going to have pi 2d squared over 4, which is effectively pi d squared over 4 times 4. So you're going to have 4 times the area. So here you're going to have 4a. Okay. And we know that these two things are equal. So FL over AX will be equal to FL over AX2 times 3 over 4. FL, A, and A. So X2 will be equal to 3/4 X, which is B. Question 19. We have 2 wires that one is made up of brass, the other is made up of steel, and they're straight in an experiment. Both wires obey Hooke's law. Hooke's law, what does it say? The force is directly proportional to the extension, provided that the elastic limit is not exceeded. So the Young modulus for brass is effectively less than the Young modulus for steel, which graph shows how the stress varies with strain. So what's so special about the Young modulus? We've talked about this. It's the ratio of stress to strain. Yeah, I know that, but why? Why is that important? It's important because the lower the Young modulus, because it's the ratio of stress to strain, is going to mean that we have a lower gradient. So the gradient is going to be lower as well. And then the higher the Young modulus, the higher the gradient. So the gradient has to be higher. This is very important because if you analyze this, you can therefore see that brass has less Young modulus. It's going to have a lower gradient. And steel is going to have a higher gradient. So it's going to be steeper. And then they both have to obey Hooke's law. So they shouldn't have any curving or anything like that. So by just observing, A and C are out. And if you're left with B and D, like I said, brass has a lower gradient, so it's going to be lower. This is less steeper than that. So the correct answer is going to be B. Question 20. A transverse progressive wave is set up on a string. The graph shows the variation with time of displacement for a point on the string. The separation xy represents what, and xy equal what? Okay. Let's understand what's happening here. Imagine you have a rope and you're moving this rope like this, right? You're like shaking it like that. You're going to have multiple particles along the rope. So this is point A, where you're standing over here, and you're shaking the rope, and the rope is attached to point B. So you're going to have multiple points along the rope over here. And this is going to result in energy being transferred. Okay, So energy is going to be transferred from point A all the way to point B. Then you can be asked to draw a displacement distance graph. A displacement distance graph basically shows you the position of every single particle. But you can also have a displacement time graph. So if we were to study closely the behavior of one of these particles, let's assume this particle, let's say it's particle A. These particles are going to be moving up and down, up and down, up and down, up and down, up and down. They always move perpendicular to the direction of energy transfer. So we can also draw a sine wave to illustrate that. But then that's not going to be a displacement distance graph. Rather, it's going to be a displacement time graph. And that will show how one particle is oscillating up and down, up and down, up and down. So that particle is going to be moving like that. So the displacement versus time graph is effectively going to show you how the one particle is going to be moving up and down as time progresses. So the moment you see a displacement time graph, your mind should be like, that's studying one particle and how it moves up and down. The moment you see a displacement distance graph, you're going to be like, that's studying all the particles and showing the relative position. So that's the difference between this graph. So a displacement time graph is associated with periods and stuff like that. A displacement distance graph is associated with wavelengths. So in this case, xy represents time period. And x and y will have the same displacements. Remember, amplitude is the maximum displacement. So this is amplitude. It's a very unique kind of displacement. So x and y will have the same displacement. So the correct answer is B. They're going to have the same time period, which is represented by the separation xy. And then they're going to have equal displacement. So point x and y just represents the different positions one particle is going to be at a specific point in time. So how is its displacement up and down changing as time is going to be progressing, like going forward, like 10, 20, 30, 40 seconds. 21. Which region of the electromagnetic spectrum includes waves with a frequency of 10 to the power of 7 megahertz? So this you're going to have to know. I can't do anything about this, so I'm going to show you the visual on my screen. That's effectively what you need to memorize. Just know the ranges for these electromagnetic spectrums. I use a little acronym. Robert Mugabe is very ugly, except grace. You can find your own way of memorizing this, but this is popular in my own context. Like a name that starts with RM is like ugly. Is very ugly, except someone with the name that starts with a G. So, this is important for you to understand how this works. So effectively, speed is frequency times wavelength. So wavelength is going to be speed, which is 3 times 10 to the power of 8, divided by frequency, which is 10 to the power of 7, times 10 to the power of 6. You do your math, you're going to end up with 3 times 10 to the power of negative 5. And if you look there, it's going to fit inside the infrared region. So with this one, I can't help you. You have to memorize this on your own. Just know the stuff, guys. You can do it. Question 22. A longitudinal wave has vibrations parallel to the direction of transfer of energy by the wave. The wave can be represented on a graph shown by the variation of the displacement of the particles with distance from the source. Which point is the center of compression? Okay, so let's study this and understand what's happening here. We have displacement away from a source, displacement towards a source, and energy is being transferred in this direction. Then we have distance from a source. What is a longitudinal wave? It's a wave in which energy is transferred through vibrations that are parallel to the energy transfer. So how this works is that you're going to have a compression, and then you're going to have a refraction. You're going to have a compression, you're going to have a refraction. So as you can see from that animation that I'm showing you, that's effectively how a longitudinal wave propagates energy. It's like, and as that happens, energy is transferred from point A all the way up until point B. Okay, so what's going on? What is the center of compression? What is happening? Compression implies two things are coming together. So if you're going to compress something, you're going to force it to become smaller. So particles are supposed to move like together, like this, move towards each other, and they're supposed to move away from each other if it's going to be refraction, which is the opposite, right? Refraction is the opposite of compression. Okay, so let's study this. So imagine all these particles from this point all the way up until this point. Imagine that all these particles are actually moving away from the source. Now look at this. All these particles are actually moving towards the source. So you have all these particles moving away. So if the source is here, let's say the source is here. Okay, let's put a speaker. Actually, let's go wild. Let's say the source is here and it's producing sound. So if you have particles moving away, they're like, oh, we don't want to be close. You have particles moving like this. Then if you're here, you have particles moving towards the source. So you have particles moving like this. You can see that these two arrows, the green and the red one, are like pointing towards each other. They're crushing each other. So B is caught up in the middle of that. So B is like, I don't want to be part of this, guys, but they're like, you have to be part of this. So B is going to be a center for compression. Right? It has no choice. So the correct answer is B. But then if you continue, and let's assume you're going to paint this over here. Again, displacement away from the source. Now look at the blue arrow and the green arrow. They're moving away from each other. So that implies the particles are going to leave a center for refraction, where particles are moving away from each other. So whenever you have particles, arrows pointing towards each other, that's compressing something, and the middle of that is going to be the center for compression, and the middle of the other one is going to be the center for refraction. This is very important because what this tells you is that that's how energy is going to vary. It's going to be compression, there's a center for compression, refraction, and we normally see this as a transverse wave graph, so we can be able to represent something like that as this, where we have displacement away from source, displacement towards source, and you can be able to see that, oh, that's how a longitudinal wave and a transverse wave are like related, because they almost show the same thing. This is all the particles, but all the particles are moving like that, like to the source. They're not moving up and down, which will be the case for a transverse wave. I hope that makes sense. Question 23. What can be deduced from a table of wavelengths of the waves in the electromagnetic spectrum? Again, I can't help you with this one. You have to memorize this. And for that one, you can easily see that the wave for X-rays is less than for radio waves, right? Green light does not have a shorter wavelength. As you can see, X-rays actually is shorter. It's over there. Red light doesn't have a shorter one. Green light you can see is over there. Radio waves don't have a radio, like they're longer. They're not going to have a shorter wavelength than infrared. 24 is consisting of two stars rotating about a common point. We have one common point and we have two stars rotating. So you're an observer on Earth standing over there, and you're looking at these light waves, and you're like, it varies between a minimum frequency, very low frequency, and a maximum frequency, very high frequency. And you've been asked to explain the change in F, the maximum frequency you can observe, and the minimum frequency you can observe when the rate of rotation of the binary star increases. So it rotates faster and faster and faster and faster. So the rate of rotation is actually omega. Omega is VR from... Okay, you haven't done circular motion. Okay, so I can't talk about this just as yet. So think about this. The rate of rotation of the binary star means the speed is increasing because it's rotating faster and faster and faster and faster. So we expect the speed to be greater and greater and greater and greater and greater. Okay, you've done the Doppler effect, I'm sure, where you said that the frequency that you observe will be equal to speed of light plus or minus the frequency of the source times the frequency of the source. Okay, so the speed, VF is actually the speed of the source of that's moving away. Okay, so the observer is stationary for the Doppler effect, then there's a source that's moving away, and as that source moves away, the observed frequency, the frequency that you see, is actually going to change between the maximum and the minimum value. So the maximum frequency that you're going to observe is going to be represented by this. Then the minimum that you're going to observe is going to be represented by this. Okay, so if you think about this, if the speed is going to increase, that means this value is going to get bigger and bigger and bigger and bigger, right? So for this case, if this value gets bigger, this overall denominator gets bigger, so the observed minimum frequency gets smaller, it decreases. And as FV gets bigger and bigger and bigger and bigger and tries to match V, the number here is going to get smaller and smaller and smaller. So F max is going to get bigger, so F max is going to increase, right? So think about this. This is quite simple, guys. So if you have 200 over 200 minus 10, right? if 10 gets to 30 to 40 to 50 to like 60, the answer that you get out is going to get bigger and bigger and bigger and bigger. And if 10 becomes like this, become bigger and bigger and bigger and bigger and bigger, the answer that you get out of this will be smaller and smaller and smaller and smaller. So we expect the minimum frequency to decrease and the maximum frequency to increase. So the minimum frequency is going to decrease and the maximum frequency is going to increase. So the correct answer is going to be C. Okay. Question 25. A teacher, very curious teacher, sets up this experiment and they want to demonstrate the double slit interference experiment. So the moment you see the word double slit interference experiment, think of this specific formula. Lambda is equal to AX divided by D, where A is the slit separation. In this case, A is equal to Q. And then as they're gonna get in, they're gonna form fringes. So bright fringe, dark fringe, dark fringe, bright fringe, and X is the distance between the bright fringe and that bright fringe. Okay. And then R is basically this D. Which change will increase this X value? Okay, so let's make X the subject of formula then. So X will be equal to lambda times D divided by A. And you can see from this illustration, in order for you to increase X, you can decrease Q, you can increase lambda, you can increase D. So decreasing the wavelength will not increase X, but decreasing Q will definitely increase X. So the correct answer is B. 26. The diagram shows two sources of waves. So we have S1 and S2. So let's put a little speaker over here. And let's put another speaker over here. So you have two speakers and they're emitting sound, and that sound is going to intersect or meet at a point P. Now, they oscillate with a phase difference of 180. So the sources are already out of phase, right? A phase difference of 180 tells you that things are out of phase. And a phase difference of 360 of 0 like shows you that things are in phase. Now, the sources generate wave of wavelength 2. Each source produces a wave that has an amplitude x0 when it reaches point P. What is the amplitude of the oscillation at P? So we're going to look at what we call the path difference. So how different are these paths? Which is literally something that you should know, guys. Okay, so the path difference in this case is one is longer than the other, which is 13 minus 5, which is 8. So if the path difference is actually n lambda, right, something you should know, that means the particles arrive in phase. So if it's lambda, 2 lambda, 3 lambda, 4 lambda, it's going to arrive in phase. And if it's not that, if it's a fraction, right, n plus or n over 2 lambda or something like that, so it's like half lambda, 3 over 2 lambda, something like that, then it's going to arrive out of phase. Something that you should just know, right? So these are facts that you should know. Okay, so 30 minus 5 divided by a wavelength, which is 2, is going to give you 4. 4, which is actually 2 lambda. So the path difference is actually multiples of lambda. So what this tells you is that they're going to arrive in phase at that specific point. So if they arrive in phase, they're going to add up together. They're going to have constructive interference. But because they are oscillating out of phase already, they're coming out of phase. They're coming with, a phase difference that's already off of 180. When they arrive here, they're supposed to be in phase, but they're not. They're out of phase because they were supposed to be in phase, but they're actually out of phase because if they were out of phase and they were out of phase here, they're going to be in phase. So it's sort of the opposite. Okay, so this phase difference of 180 reverses whatever you had. So if they were to arrive here out of phase, because they're actually out of phase by default, this change that made them out of phase basically put them in phase, right? Because they're already out of phase here. So if they're out of phase here and they are going to arrive at P out of phase because of this motion, this 13 and 5, that's a different factor. They already came out of phase, but this is supposed to put them out of phase again. So instead of putting them out of phase, it's going to align them and put them in phase, right? And if this was supposed to arrive in phase, right? This was supposed to put them in phase, but because they're already out of phase, if you try to put them in phase, you're going to just take them out of phase again. So if particles, because of wave differences, like of path differences, are supposed to arrive in phase, if they are in phase, fine, they also arrive in phase. If they're out of phase, fine, they will arrive at this point in phase. So effectively, the amplitude of the oscillation at P is going to be 0. Okay, so this is very difficult to explain. So it's going to be destructive interference occurring. So they're going to arrive at P out of phase, and they're going to destroy each other because they were supposed to arrive in phase, and they can't because they already came out of phase. I don't know how to explain this, but okay. Think about it this way. Out of phase means that the path difference might be lambda, half lambda. Okay, so they're coming with half lambda, and because of this, the path difference is 2 lambda. So half lambda and 2 lambda is going to give you 3.5 lambda, which means they're going to arrive at P out of phase. And if they were supposed to arrive here with half lambda, with 3/2 lambda maybe, half plus 3/2 is going to be 4 lambda. So if they're supposed to be out of phase at this specific point, at P, 3/2 lambda, because they're already out of phase, they already came with half lambda, it's going to add up and give you 4 lambda, so they'll actually be in phase. But if they came with like 0 lambda, and they were supposed to be 3/2 lambda here, it's just going to remain at 3/2. 3/2 plus 0, 0, because they came in phase. And if you're supposed to be 4 lambda, it's just 4 lambda. But it's only when you come with like out of phase already, which is half lambda, that if you're supposed to have a path difference of 3/2 lambda, you're going to have in phase. If you're supposed to have a path difference of 2 lambda, you're going to have out of phase. I hope that makes sense. It's a little bit tricky. So if they arrive out of phase, because the path difference is going to be 2 lambda plus half lambda, which is 3/2 lambda because they're out of phase, they're going to experience destructive interference at that point because they come out of phase, and the total amplitude is going to be 0. Okay. A pipe closed at one end has a loudspeaker at the other. A stationary sound wave is formed in the pipe within the pipe, and it has an antinode at one end. The length of the pipe is that, the speed of sound is that, which frequency is not going to produce a stationary wave. Okay, so you're going to need to understand this. So the first simplest wave that you can produce is like this. So with this one, you have a node and an antinode. That's the simplest one that you can produce. Okay, we know that V is equal to F lambda. So we want to find the smallest frequency that you can have. V divided by lambda. Okay, so V is 340. And you want to find lambda. So we know that antinode, node, antinode, node, antinode. So we know that from an antinode to this antinode is lambda. So from an antinode to a node, that's going to be a quarter of a lambda. So this distance is going to be a quarter lambda, which is 0.85. So lambda is going to be actually 0.85 times 4, which is going to give you 100 hertz. Okay, and if you want to upgrade this, the wave that follows exactly after this one looks like this. That's the next one that follows. You just keep on adding nodes in between, right? So you're going to have a node here, you're going to have a node here, and you're going to have an antinode here. So it's antinode, node, antinode, node. So this one, which is actually 3/4 lambda, which is equal to 0.85. So in this case, my frequency is going to be 340 divided by 0.85 times 4/3. If you punch that, that's going to give you 300 hertz. And if you do that, the next one that follows, you just add another node in between. So you're going to have 2 nodes. So one node, another node, just 2 nodes. So this should be like symmetrical, but you get the point. You have node and you have node. You can find another one. You can go ahead and put 3 nodes, 1, 2, 3, something, and then they keep on just doing that. So you see, we went from 100 to 300. It's going to get higher and higher and higher, and 500 will actually be produced, but we can't get 200 because we strictly went from 100 to 300 hertz. I hope that makes sense. So we're just looking at common points that we know, we start with this easy one, which is like this, where we have an antinode and a node, and you find the frequency that you get. You go to the next one, which is effectively something like this, and you figure out that we've gone from 100 to 300. So 200 will not be produced. If you bring about a loudspeaker with 200 hertz, it's not enough for you to have a stationary wave produced inside of there. Question 28 is electric fields. We don't do that, so we won't answer that. Question 29 is electric fields again, so we won't do that because you don't need to know that, for your syllabus at least. Question 30. The current I is given by this expression. What does N represent? N represents the number of free electrons per unit volume. You should just know that. So I is the current. A is the cross-sectional area that current is flowing through. A is the number of free electrons, emphasis on free, not the total number of electrons, but rather the free electrons that are available to move. And V is the velocity. And Q is the charge of an electron. And yeah, that should be it. Third one, what is the ratio of power in lamp X to power in lamp Y? Very simple. You're given resistance and current and you're asked to find power. Guys, come on. Power is VI. But power V is IR, so power is I squared R. So power in lamp X is actually I squared, 0.50 squared, times R, 9.6. Power in Y is 3 squared, times 1.2. Okay, you punch that in, and you get 0.22, which is A. 32. A cylindrical piece of soft wire has a resistance R. It is rolled so that its length is doubled, but the volume stays constant. Remember, volume is area times length. Okay, so if you have this area and something this long, so this area times that length is going to give you the volume. Okay, so you want to find the new resistance. So initially, resistance has this formula, resistivity L over A. Okay, so if you're going to double the length, so V new, if the new volume is going to remain the same, if you double the length, you have to halve the area. Like it's known, right? You can't keep the volume the same if you double the length unless you halve the area. So it's a code word of saying we have doubled the area, but we've doubled the volume, we've doubled the length, but we've halved the area. So if you go here, the new resistance will basically be, because it's the same thing, resistivity is also a property that remains constant, double the length, half the area, so the half goes above, so you're going to have 4 rho L over A. But rho L over A is R, so you're going to have 4R, which is going to be D. So effectively, you're looking at this and you're saying, for the volume to remain constant, if I double the length, I have to half my area. And then you go and say, okay, so if I double the length and I half the area, the half flips, becomes a 2. So you're going to have 4 times the original resistance that you started with. The sum of electrical currents, so if you have a point, the sum of electrical currents entering that point will be equal to the sum of electrical currents exiting that point. That's Kickel's first law, guys. Kickel came up with these laws, and it's a conservation of charge. Charge cannot be created nor destroyed because current is the rate of flow of charge. So you can't have more charge than you started with. Where did it come from? That's Kickel's law. 34. What are the values of the current I1, I2, and I3? Okay, this is fun. So we're going to apply Kickel's second law to solve this question. So if you look at this, how does Kickel's first law, second law work? You create a loop. Okay, so you consider this as one thing. That's loop 1. And you consider this as another thing. That's loop 2. Okay, so let's start with loop 1. So for loop 1, you have a power source of 15 volts. But that 15 volts is distributed towards a 2 ohm resistor. So the voltage drop, V is equals to IR, is going to be 2 times I1. Plus, you're going to have a voltage drop across that 2 ohm resistor moving with I2. Okay. Let's go to loop 2. Loop 2 is this one. You're going to have a 9 ohm volt supply. And you're going to have 2 and I3. And you're going to have 2 and I2. But you're going to see that these two equations are not enough because, well, they don't really help me a lot. But if I look at this point, I have I3 coming in like this, I1 coming in like this, but going out is I2. So from Kirchhoff's current law, which is the first law, I1 plus I3 should give me I2. Straightforward, right? Okay, so you have three equations that you can play around with. And if you play around with these three equations, you're going to find the answer. So let's do that. If you look at equation 2, so let's call this equation 1, equation 2, equation 3. Okay. If you look at equation 3, we have I2 is equal to I1 plus I3. So if I can remove I3 in equation 2, I3, which is effectively I2 minus I1, and I can remove I3 in equation 2, I can have, if I divide throughout by 2, that's 4.5 is equal to, 4.5 is equals to I2 minus I1 plus I2. So you're going to have this beautiful relationship, which says 4.5 is equal to 2I2 minus I1. So let's say that's equation 4. And if you look at the first equation that we had 15 is equal to 2I1 plus 2I2. Now, this is very straightforward, guys. So effectively, 2I2 is 15 is equals to plus I1. So 15 minus 4.5 divided by 3 is equal to I1. So I1 is going to be 15. That's 3.5. So I1 is going to be 3.5. Then if I1 is 3.5, I know that 15 is equal to that. So 15 minus 7 divided by 2 is going to be equal to I2. So I2 will be equal to 4. Then I3 is 4 minus 3.5. So I3 will be equal to 0.5. So the correct answer is going to be C. Okay, so what we're doing here basically is creating two loops. So you need to know how to use Kirchhoff's second law, which says within a closed loop, the sum of the potential differences is equal to the sum of the EMFs. So in this case, 15 should be equal to the sum of the potential drops that we experience in loop 1, then in loop 2. Then you apply Kirchhoff's third law, Kirchhoff's first law, which is the current law, and then you combine all the three to get your answer. 35. What is the current in resistor X? We're given this little nice circuit. This is beautiful, very beautiful, because I'm given resistance and I know that V is equal to IR. So in order for me to find the current, I just need to find the voltage value. Okay, so these two things are in parallel. And for things in parallel, the total resistance follows a specific formula. 1 over RT is equals to 1 over R1 plus 1 over R2. Then product over sum. So R1 times R2 over R1 plus R2 should be equal to R total. So it's just a way of you easily finding the total resistance for two resistors. Just important for you to know this. If you find the product of two things divided by their sum, you get the total resistance. So in this case, 4 times 4 divided by 2 plus 2, that's going to give you 4 times 4, that's 16. 16 divided by 4 plus 4, that's going to be 8. 16 divided by 8, that's going to be 2. Okay, so you're going to have V over 2000. and you want to find the voltage across these components. So what's going to happen is your circuit is going to look like this, where you have 6 volts, and you have 4, and you have 2. And if you want to find the voltage across this guy, you can apply the potential divider law. So 2 over 2 plus 4 times 6, 2 volts. So in this case, we're going to end up with 2 volts across these guys. So 2 volts across here, 2 volts across here. And if you're to find the current flowing through these 2 guys, like current flowing through here, you could have easily used this. R is 2000. But in this case, we're going to use 4000 versus the resistance towards X that we're interested in. And because they're in parallel, they're going to have the same potential difference effectively. So we're going to have V divided by 4000. So 2 over 4000, that's going to be 0.50 milliamps, which is B. Okay. 36. A uniform resistance wire of length XY is connected in series with the cell L. Another cell M is connected in series with the resistors of resistances 5, 10, and 15. The potential difference between P and Q is balanced against 12.5 centimeters of the resistance wire, so the ammeter reads 0. Okay, so we want to find which balanced length of resistance wire corresponds to what. Guys, this was one of the easiest questions you're going to meet. So let me show you how easy it was. So between P and Q, you had 5 ohms, and 5 ohms corresponded with 12.5 for it to be balanced. So between P and R, how many ohms do you have? Right? Between P and R, you have 15, because P and R is here. All right? So P and R is 15. So you're just supposed to say 15 ohms is equals to what? That's more. So 15 divided by 5 times 12.5, that's 3. Times 12.5, that's 37.5. Then you're going to go for Q and R. Q and R, we have 10, so that's Q. That's R. Like this. How much length do you need? So it's 10 ohms. So 10 ohms will be equal to what? So it's 10 over 5 times 12.5, and that's going to give you 25. Right? Very simple. Then P, Q and S. Q and S is 25. So Q and S is going to be equal to 25 divided by 5 times 12.5. That's going to give you 62.5. So the correct answer is going to be Q and S, 62.5. P and R, 37. It's going to be B. Very simple. Question 37. A motor is required to operate at a distance of 800 meters from its power supply. The motor requires a potential difference of 16 volts and a current of 0.60 amps to operate. 2 wires are used to support power to the motor as shown below. You have a power supply, you have 2 wires, you have that distance, and you have that motor. Okay. I can redraw this and be clever, right? So I can have my power supply, which is, let's say, 16 volts. So the question is literally asking me the minimum output PD of the power supply. Okay, so I don't know it. It's going to be X volts. Fine. So here you have wires that are having a certain resistance in them. So I can put a little resistor here to indicate the wires on both sides. Right? This is very important. So if you look at this, we have 800 meters worth, and each one has 0.005 per meter. So we can symbolize this with 800 times 0.005, and this one will also be 800 times that. Okay, so you can redraw this and make it look like this. So this one requires a current of 0.60 and a voltage of 16. So if there is 0.60 entering into this, what is the voltage that you experience across that? So the voltage in wires will be equal to 2 times 800 times 0.005 times 0.6, because you're trying to find the voltage drop V across these wires, which is just the same. So it's 2 times IR, the current times the resistance. So this current times this resistance, something like this. So effectively, if you get the voltage across the wires and that's 16, you add them together. So that's 16 plus 2, 800 times 0.005 times 0.6. Effectively, if you were to find this out, here you're going to get 4.8. So 16 plus 4.8 is going to give you 20.8 volts, which is D. Which elementary particle is a lepton? So a lepton is basically a particle that doesn't experience a nuclear force. So an electron is very far away from the nucleus, so it's a lepton. Proton is not, a neutron and a quark are not, because they're very further away from the outside of the shell. They're actually closer to the nucleus as you can possibly get. So a lepton is basically a particle that doesn't experience a strong nuclear force. So we can say that an electron is effectively a lepton. How many down quarks are there in a nucleus of hydrogen? So hydrogen nucleus, like this, consists of 1 proton and 2 neutrons. But a proton effectively consists of 2 up quarks and 1 down quark. This is a structure that we just know. We found this. And a neutron consists of 2 down quarks and 1 up quark. Okay, so if you have 2 neutrons, we're going to have 4 down quarks. 1 proton, you're going to have 1 down quark. So in total, you're going to have 5 down quarks. The correct answer is going to be D. 40. What is the correct equation for beta plus decay? So, well, this we just know. Like, we don't need to study this. We just know that a beta plus decay is when we have a proton that turns into a neutron, forming a positron and electron neutrino. And that'll be it. Thank you guys for watching, and I'll catch you in the next one.